Nielsen form before? Anybody even hear of the Nielsen form? Do you have any idea what it's good for?
No, nothing.
Guess what? I don't either.
Good
I
for
looked it
nothing,
up on
huh?
the web. I meant to do it sooner, but I had a meeting this morning and then I was just Googling through on it and I couldn't find where somebody said, oh, the Nielsen form is really good for.
This situation. Yeah, it's funny how they like just have you write that stuff.
And, well, it turns out there is a whole history of writing Lagrange's equations in different forms. So what the hell did I do with that?
I'll write in Lagrange equation in different form, have it named after me, and not have it be used for anything.
Yeah, I mean, that's one thing that drives me crazy in this business is you have to know the names of all of these different sets of equations. And
Do you really?
They couldn't really name everything Euler though.
right, Euler sure got his name on lots of things. But when I looked up on the web about Nielsen's equations, it turns out that I found in just a few minutes Googling at least a half a dozen different forms of Lagrange's equations. And I'm unclear as to where they're used. Here was one where a guy in '75 published a paper talking about, he mentions the Nielsen form and talks about the motion of an artificial Earth satellite with constant speed and what he calls Appel's example. There's also Appel's equations, which I haven't had time to look into and probably won't. But Appel sets up the equations where they define a new S, which is not the action, which is 1/2 the sum over Q's of 1/2 m a dot a. So it's the acceleration 1/2, and instead of mv squared, kind of, and they call it the acceleration energy form. And that's Appel's version. And you can set the whole damn thing up with these, using the accelerations instead of the velocities. Kind of weird. So I honestly don't know where and why people use some of these different forms, except that I saw some passing reference that Nielsen's form may be useful for describing exploding plates. So,
I'll keep that in mind next time I go discus.
next time, right, next time
Sounds
you're
like a midterm question.
making an IAD. So anyway, who would like to do the derivation on the,
Called dibs.
on Mr. Nielsen's equations? And this is definitely where you need to keep track of your, as I'm sure you all struggled. Stephen, you had a nice derivation, I think. You want to do it?
John.
I'm sorry, John.
Asked to do it.
Huh?
John
No,
wants to do
Stephen,
it.
I'm sorry, I got you guys confused.
He can do it, it's fine. I'm pretty sure his is similar.
Oh, okay. Sorry, guys, I'm not fast with names, I should have.
It's underneath the purple paper, it looks like.
Under the purple paper. Okay, John,
Yeah.
go for it.
All right, cool. Okay. And so as you say, we got to be very careful with the indexing. So, yeah, if you want, I can start over there. Okay. So we have from equation 153 in the book, dEt of dT dq dot j minus dt dqj is equal to qj. I mean, that's just separating the Euler-Lagrange formula in terms of t and u. But we were asked to consider the Nielsen form. dt dot dq dot j minus 2 dt dqj j. Now these two equations are equivalent. And if we expand this out, what we have to show effectively is expanding this out. We have to show d dt dq dot j is equal to dt dot dq dot j minus dt dqj. That's what we have to show. Expanding it out to these two equivalent. So, what we proceed to do is we just we're just very careful in our chain rule. Okay?
That's the key.
Right. So let's first, given that we have to look at T dot, let's go ahead and expand that out. T dot is the time derivative of the kinetic energy. And so that is partial derivative with respect to time. It might depend on time. Normally, well, we don't see that, but it can. And then, let's see. We also say that the kinetic energy, being part of the Lagrangian, can also depend on the coordinates and their corresponding velocities. So like that. Now, Nielsen's equation. Let's see. Right. We also have that we want to take the derivative, the partial derivative of this change in kinetic energy. Now, here's something that was sort of driven into me some years ago. Is that whenever you're taking a derivative with respect to a variable, you shouldn't, just jump to doing the same index. You can run into some hairy things that way. So, as a safety precaution, you take the partial derivative with respect to another variable, and then you have a Kronecker delta resulting. So, this first term, we have this is the partial derivative, and by the property of, what is this, Q dot? Yeah, this is Q dot. Yeah, by the property of partial derivatives, we'll eventually say that these commute, but given that, I'll just write it out like so in shorthand. And then when we take the partial derivative of, with respect to Q dot J of these variables, we get a dqi dot dq dot j, which secretly is the Kronecker delta Kronecker delta. And then you have dt dqi plus qi, and then again I'm going to shorthand it. dq j dqi, and this is dependent on the acceleration. So if we were to take the partial with respect to the acceleration, that would just go to 0. So we only have one term contributing for this. Okay. So, we just have that as a simplification. And then we just also look at, let's see here. Yeah, so we took the derivative of qi dot. Okay. And now, we just also proceed to consider the partial derivative with respect to q dot. dt QJ, like so. And we'll just expand the time derivative out like we did up here. So that's d squared t dt dqj. And then we just again expand out here. Let's see. Q dot I d squared t d squared qi partial with respect to qj, and then q double dot I d squared t dq dot I dq dot j. Right? And with our terms?
Think so?
Yeah. But basically, at this point, you can actually relate these two quantities because of the, the property of the commutativity of partial derivatives. So this term is equal to that term. And let's see here. This term is equal to that term. That term is equal to that term. And so what's left over, and once the dust settles, is you have this minus, because of that Kronecker delta, of dt dqj. Yeah, so once the smoke clears, we have dt dot dq dot j minus dt dqj is equal to dt dt dq dot j? Yeah. And did I drop a code? Yeah, this should have been a dot. That's fine. Yeah. But it all works out, and that's what we set up to prove.
Right. Now, can the mass be a function of time in this
Oh, yeah.
setup?
Yeah, one I like to look at, and it's also in Goldstein, is the Calderola-Kanai Hamiltonian, where you have like an exponentially decaying mass, and you just look at it in the harmonic oscillator case.
Okay, good, nice. So most people didn't get fancy with the variable indices, but can't quibble about that too much. Okay. So let's go on to the problems that we're due for today. And so the problem number 9 is showing the gauge invariance. I guess John certainly has not gotten to that yet in E&M, if you're taking E&M now. At any rate,
He'll get there quickly.
Because I need to get the first
Hmm?
one.
So he'll get there quickly.
he's taking off at a good pace.
Oh, I don't know, I just remember predicting it last year.
Thank you.
Okay. Okay. So does somebody want to do the gauge invariance problem? Get started.
Sure. Okay, does everybody have their homework?
I can do that one.
Okay.
You're talking about number 9, right?
Yep, you're up. Don't be fixing up your own solution now.
As I'm going along.
Oh boy, lots of work.
Is that what today's go over? Is that what today's?
Yeah, so the gauge invariance is...
No, I mean, are we basically just what we're going to do today?
Oh, sure, okay.
So I like this idea. This is a small enough class that we can do this. You get up and gives everybody some experience talking on their feet and so on.
Well, are we gonna be, so I kind of read the second chapter of Landau and I was kind of confused about mechanical similarity. Are we gonna hit that maybe Friday?
I was thinking to go through that, yeah.
Huh.
I mean, the more
I was kind of lost, and I was also kind of like shocked that Kepler's laws and then the
that
spiral
they-
theorem just kind of
they
fell
fall
out.
just boom, boom, boom.
Yeah, let's describe all the stuff you've learned over the last 5 years in one chapter
One page.
by changing K. I was kind of pissed about that.
Okay, I'll go through that on Friday then. Because again, it's one of those beautiful things, but nothing you would invent quickly.
Okay. So for this one, it consisted mostly of me staring at it and then remembering a definition of that Goldstein gives, and then what the total time derivative looks like, and that kind of just falls into place. So for Lagrangian, it's the kinetic energy minus the potential energy. And the kinetic energy is just 1/2 mv squared. So this gauge transformation actually doesn't change your kinetic energy at all. The entire change comes from your potential term. So basically, you get that your L prime is just your original Lagrangian, which is just the A and the phi terms, minus the additional terms that you get here. So just writing it down quickly, you get it's that. So, and again, this comes from what he already had written down in the problem. So when you do that, you can rewrite, I went through this a little step by step in my work, so I'm going to skip a little bit just because you guys can keep track of algebra, I'm sure. So anyway, if you remember from the previous problem that was just shown, that the total time derivative
Is he missing a fee? Is he missing a fee?
is,
No. I don't think so.
Oh, okay, he skipped.
I should write this down properly so it looks right when I go through it. Something like that. And if you look at it that way, it starts to look a lot like partial psi, partial t, plus the, I'm going to skip a couple steps here, actually no, I better not, just make sure it comes out right. So you get please let me know if you can't read my handwriting if you have a question. So you basically start to look like that. This, and this are the x, y, and z components of that velocity that we've got here. So this actually equals that's I, because each one of these is the differential components of psi along x, y, and z respectively. So you pull out x plus by plus z and these two, and you get v dot grad psi. So then your Lagrangian, your new Lagrangian, when you remember what this looked like, d psi dt is equal to, and we just showed this partial psi partial t plus the velocity dotted with the grad t, so you get it's the old Lagrangian plus q over c plus d psi dt, and an equation, was it 1.57 or something like that? That's what it was on the homework, so I hope that's what it is. Goldstein says that if you have L prime of Q dot and T is equal to another Lagrangian for the system that's already been established as correct, which is what we have, plus the time derivative of some function that it also satisfies the original system you're describing. So as long as f is differentiable, so that's basically what it is. Because we showed that this gauge transformation basically just reduces down to the total time derivative of this scalar function. And as long as you can add a differentiable scalar function with respect to time to any Lagrangian for the system, you still get suitable Lagrangian by that equation you described.
Comments?
So, Lagrangian that you showed us, the T minus B, that's just a Lagrangian that works. And then could be just a whole bunch, depending on like a bunch of different transformations.
Oh, yeah.
Is there a best Lagrangian, or is that the T minus B?
The one that you can write down the fastest?
Yeah.
Right, and that's a very good question, because what this is really saying, this phrase gauge invariance is something you will hear more of, especially when you start taking field theory, because gauge invariance turns out to be a very major property in constructing new theories. And although, well, it is pretty much what we're saying here. The idea of gauge invariance comes from the originally the mechanical idea that it doesn't matter. We can set the potential anywhere we want. It's independent. All of the equations of motion are independent of what measure that we take for the whole thing. We can offset the potential by a constant. We can fool with the gauge of the system. And just as we were talking about in the Landau derivation, that we can multiply everything by constants, we can't get away with adding arbitrarily to one part and not to another. That changes things relatively. But if we screw the gauge, we can have a lot of freedom. And that fooling around can include some pretty complicated functions, which, if they satisfy being a complete time derivative, are not going to affect the Lagrange's equations of motion.
So I was trying to do this, I don't think I was completely successful, but you can plug the second term right into the Euler-Lagrange equation and it'll go to 0, is that correct?
Yeah.
Like the two terms will cancel, I think.
I think that's what
You're
it's
saying from this,
Or right to your left. Yeah, the extra term, I think, if you plug it in, it goes to 0, and then you basically show the equations of motion are constant.
I imagine, yeah, that's what would happen. I mean, I didn't prove this myself. I just said,
Yeah.
oh, there it is. I'm going to use that. I figured it's in the textbook. We can.
But he's
use it without
done.
showing it,
He's
but-
shown that that's the whole time derivative.
Yeah.
Game is over.
Yeah, I'm assuming it has some property to do with solving partial differential equations.
I mean, you did most of the work, I think, with your...
Yeah, the only thing that I didn't prove explicitly is why this is true. It's a different book, and I'm sure that there's something
Well-
that if I ran it through, yeah.
I think I did put it plugged into the Euler-Lagrange and it comes out 0.
Yeah. I'm not complaining, just
Right.
Ah,
So
good question.
saying.
it's just a fancier statement than this idea that the potential energy is an arbitrary value. It turns out that it's more, you can add something much more general than that, as long as it's a complete time derivative of any reasonable function, that it won't change the equation of motions, which is, it's a little hard to chew, actually, right? I think, Jesus, if I got something in there that's changing with time, isn't that gonna muck the works up? Apparently not.
Sounds like a math proof.
Well, it certainly is, it certainly is. certainly is.